Welcome to the walkthrough of the 2024 GCSE Combined Science foundation paper for chemistry, and we're looking at paper 2 today. Now, the first question is all about the Earth's atmosphere and how it's changed during the last 4.6 billion years. So question 1.1, what is the approximate percentage of nitrogen and of oxygen in the Earth's atmosphere today? Draw one line from each gas to the percentage of that gas. Now, there's 2 marks available, and we can only draw one line from each of the gases. This is just something you need to know. Nitrogen it's actually about 78%, so nearest number there is 80%. Oxygen is actually 21%, so again, nearest number there is 20. There's no other way to get the 2 marks there, relatively straightforward. Then on 1.2, the approximate percentage of carbon dioxide in the Earth's early atmosphere was about 95%. So which of the 2 reasons why the percentage of carbon dioxide has decreased since Earth's early atmosphere? Now, you've got to pick 2 boxes. So make sure you're ticking 2 boxes. Don't think they're trying to catch you out and you know better, and tick 3. So combustion of fuels, well, that just adds to carbon dioxide in the atmosphere. Deforestation, again, generally leads to more carbon dioxide being there because we're losing trees which take in carbon dioxide, which is a bit of a clue for later on. Now, dissolving in oceans. So 70% of the planet's covered in water, and that is a huge surface for water to dissolve in. Sorry, carbon dioxide to dissolve in. So that is definitely a good answer. Photosynthesis, well, that's where plants take in carbon dioxide. And again, that is the other reason that the carbon dioxide level dropped significantly. Remember, respiration, we carry out respiration, and it's where, in part, we breathe out carbon dioxide. So that's clearly an incorrect answer. Make sure you're only ticking 2 answers, though. All right, question 1.3. So we've got a graph now showing the change in the percentage of carbon dioxide in the Earth's atmosphere from 1800 all the way through to 2020. So you've got the percentage of carbon dioxide in the Earth's atmosphere as your y-axis, and you've got your year on the x-axis. Now, we've got 3 marks up for grabs, so we're going to need to do a little bit of work here. Now, the first point to get it, and remember, we're just being asked to describe the trend. So we don't need to talk about science behind it. It is purely tell me the story of what that curve is showing. Now, to begin with, the line is flat. So it means that the level of CO2 is constant until, I would say, starts to change around about here, until about 1850. After that, it then increases up to 2020. Now, where do you get the marks from? So if you talk about the constant level to begin with, there's 1 mark, until around about 1850, and they'll give you a bit of leeway on that one, so anywhere between 1850 and 1865 will give you the 2nd mark. And then if you talk about the kick up, that extra increase up until 2020, there's your 3rd mark as well. So that one is very much look at how many marks are available and use that information to help guide you as to how much information you need to give. Question 1.4, which one of these is also a greenhouse gas? We know carbon dioxide is a greenhouse gas, but this is another one of the ones that you just need to know. And the answer is methane. So that one, you just need to know that carbon dioxide is a greenhouse gas, as is methane, as is water vapor as well. They're the 3 you need to know. And then question 1.5, which of the following is an environmental problem caused by greenhouse gases? Now, acid rain is an environmental problem, but it's caused by sulfur dioxide or nitrogen oxides. So that isn't due to greenhouse gases. Global dimming is due to particulates having lots of soot in the air. So it's definitely not that. Climate change. So anything like global warming, climate change, that's where your answer needs to be. Right, next one. And then we're just trying to get some maths into this question. 1.6, calculate the relative formula mass of carbon dioxide, CO2. Now, you don't even need your periodic table here because they are giving you the relative atomic masses. Now, CO2 means we have one carbon and two oxygens. So you need to do 1 times 12, that's the mass of carbon, plus 2 times 16. That would give you 12 plus 32, and that will give you an answer of 44. You get 1 mark for showing you're working, second mark for showing the correct answer. And that whole question is out of 11 marks, so hopefully you got 11 out of 11. Good start. Now, question 2, we're on to chemical testing here. Different tests can be used to identify chemicals. We've got some melting points of 4 different substances, and we've got the results here. Now, which substance was pure, and we have to give a reason for our answer. Now, remember, the melting point of a material is sometimes called the fixed point, and it's a specific value for a pure substance. Now, if you look at A, C, and D, they all give a range of values, which tells you that the substance is not pure. The only substance that gives an exact value is B, which means that it is pure. And the reason is because it has a specific melting point. Now, to get the 2 marks, obviously you need to get the correct substance first of all, and then the correct reason. If you put A, C, or D, doesn't matter what reason you put, you're going to get 0 marks on that one. And then question 2.2, we're looking at copper sulfate, anhydrous. Think about what that word means. An means without, hydrous is to do with water. So anhydrous copper sulfate can be used to test for water. Word equation is given to you below. We need to complete the sentence, and they'll be nice at giving us some possible colours to use. When water is added to anhydrous copper sulfate, the colour changes from white to those blue crystals that you all probably made when you did paper 1. So definitely white to blue. And then on question 2.3, the reaction between anhydrous copper sulfate and water is reversible. How does the word equation show that? Well, it's the sign. You've got that reversible sign showing like a backwards and forwards type thing. That's all you need to put to show that this is a reversible reaction. Right, and then question 2.4, that we are given the formula of anhydrous copper sulfate. It's CuSO4. What is the total number of atoms in the formula? Right, so we've got Cu, anyway, it's Cu1, S1, O4. 4 plus 1 plus 1 gives you 6. Nice easy mark. And then for the last part of this question, chlorine is a gas. Describe the test for chlorine, give the results. Now, what you would do is you would or place a piece of litmus paper into the gas, or hold it at the test tube where the gas is being produced. Now, it doesn't matter if you're using blue or red litmus paper. The result is that the chlorine gas bleaches the litmus paper, so it will go white. And that's your test for chlorine. Right, so that question is out of 8 marks, so well done if you got all 8 again. Now, question 3, we're looking at printer ink, and it's a mixture of chemicals. Now, question 3.1, what is the name given to a mixture that has been designed as a useful product? This is probably the worst definition ever, but it's just one that you need to know, and it is formulation. Comes up every year, and just whether it's a case of what do we call in this form, it's formulation. how do you define a formulation? And it's often a tick box, but just make sure you know that particular answer. And then we're on to chromatography. So we're going to carry out chromatography of the colours in the printer ink, and you've got your chromatogram, which is figure 2 on the left there. Now the student used a ruler for the start line. What would the students have used to draw the start line? Give a reason for your answer. Well, if you remember, the one thing you need to do this in is pencil. Why is that? So that the pencil lead is insoluble. So the pencil doesn't dissolve into the solvent. So that's just going to, because if it did, it would just add impurities to the answer, and it would affect your results. Now, you've got to determine the RF value of the red colour. So it's this red dot here. And we're going to calculate the RF value, and they're even giving you the formula. So the distance moved by the colour divided by the distance moved by the solvent. It even breaks it down. So the distance moved by the red colour, you would get your ruler and measure the distance from the start line to the centre of the red dot. Now you've got to be careful on how you've printed out your exam paper, because sometimes it prints out different sizes. But going from the mark scheme, the distance moved by the red colour is 3.2 centimetres. Distance moved by the solvent, again measured from the start line to the solvent front, and that comes out as being 8 centimeters, 8.0. RF therefore equals 3.2 divided by 8.0. Put those numbers into your calculator and it comes out quite nice as 0.4, and you're getting 4 marks for that. So you get a mark for each of your measurements. You get a mark for putting them into the RF formula, and the 4th mark for getting the correct answer on that one. So well done if you got 0.4. Remember, with RF value, the value can never be greater than 1. You can't have your colour moving further than the actual solvent. So if you end up with something above 1, flip your numbers the other way, and the chances are you'll probably get it the right way around after that. Right, so question 3.4. Now we're given some different blue colours and their RF values. Now the student determined that your RF value of the blue colour in the printer ink was 0.86. Suggest which colour was used in the printer ink. Now we just need to look at the table and look for a value near to 0.86. Well, clearly 0.88 is the nearest value, so there's a good chance that the Prussian blue colour is the one that was used, and the reason is it has the nearest RF value to the printer ink, or to the 0.86, and that's the kind of answer you need to give. Now again, that question is worth a total of 9 marks, so well done if you got all 9 of them. Right, so now we're going to look at drinking water. So tap water must be safe to drink. That's good news. 4.1, what name is given to water that is safe to drink? Well, I don't know about you, but I'm not sure I'd drink out of groundwater. That's kind of just water lying around. Wastewater, that doesn't sound very pleasant. So the only possible answer there is potable water. It's just one of those definitions you need to remember. All right, 4.2, water is sterilised to make the water safe to drink. So which of the two ways of sterilising that drink of water? So remember, we're ticking 2 boxes. Work your way through it. Carbon dioxide, well, no, that's going to make your water fizzy. That would be carbonated water. Electrolysis, well, we don't want to split the water apart, so it's definitely not that. Filtering, the water should have been filtered already. That's not good enough to actually fully sterilize the water. That would just take out some big lumps out of it, which means we're left with ozone, which is definitely something that's used to sterilize water, and so is UV light. So it's those bottom 2 answers. Remember, you need to tick 2 boxes, then you're going to get 2 marks. Okay, so for question 4.3, we're now into one of the required practicals here, and we're investigating the mass of dissolved solids in samples of river water, seawater, and tap water. So you've got the whole method there, which you need to read through. Now, question 4.3, which is the most suitable equipment to measure 100 cubic centimeters of water? We've got to tick one box. Well, which is the most suitable? Well, measuring cylinder is going to give you the most accurate and precise answer on that one. Question 4.4, we've got a little bit of maths to have a go at. So we've got some results. So we've got 3 different types of water. We've got the mass of the evaporating basin at the start, and then you've got the evaporating basin with the dissolved solids. So that's after we've evaporated the water. To get the mass of the dissolved solids, you need to take that number away from that number, and that's where they get the 1.0 from. So we just need to do the same thing for the seawater. So the calculation is 114.0 minus 110.5. If you need to use your calculator, do so, but you should get an answer of 3.5 grams. Only worth 1 mark because it's a relatively straightforward calculation. Okay, now moving on to 4.5. So this is our variables, which can come up in any paper. We need to identify a control variable and the dependent variable. Now remember, control variables, what do you keep the same? What do we control essentially? And then the dependent variable is what you measure. So what are we measuring as a result of our change of the different types of water? So if you look at that, we are measuring the mass of the dissolved solids. Now, what do we keep the same in every experiment? Well, the mass of the evaporating basin, that doesn't really matter because we took that into account. Room temperature, that doesn't affect anything other than water might evaporate a bit quicker, but it doesn't affect our results. Well, the type of water, that's what we've changed. So that's actually our independent variable. So we need to make this a fair test. So we need to be using the same volume of water in each case, and there's your control variable. So again, only one line drawn from each of the variable boxes to one of the examples. 2 nice marks to get. Then following on from that, graph drawing. Graph drawing you should be looking at as being, relatively easy marks. Now we've got the mass of the different types of ions dissolved in 1 decimeter cubed of seawater, so you've got the values there. Now they've actually plotted calcium for you already. Now we need to complete figure 3. Now you've got a checklist, and I would suggest you actually use it as a checklist. Complete the scale for the y-axis. So that seems to be going up in half a gram for each of those double squares. So, this is a relatively easy mark. I'm going up to 3.0. So don't forget that bit. I would tick these off as you do them. So we've completed that. We've done the y-axis. Plot the data from table 4. So we need to have magnesium. So we're going to have Mg down here. So that's going to go to 1.3. So you're going to have the advantage of having a ruler. Just be careful with these scales because 1.3 is going to go up to here. So we're going to draw in that you have the massive advantage of using a ruler and get much straighter lines. We also need to do the sulfate ions, so the sulfate bit down here. That's going to go up to 2.7. So that is going to be one little square from the half, and again you've got your column drawn in there. Now it's important that you are accurate with how high your bar actually goes. There's a tolerance of plus or minus half a square. So, make sure you are working precisely when you do this. Plot the data, we've done that. So there's 3 nice marks. Now, you get 1 mark just for doing that bit. Your 2nd mark for labeling and plotting magnesium properly. Your 3rd mark for plotting and labeling the sulfate ion as well. Like I said, this particular question really has got nothing to do with science. It's purely a maths question. Now we're on to question 5 now. This is all to do with life cycle assessments and recycling and so on. So we've got just a reminder that life cycle assessments are used to assess the environmental impact of different products. Question 5.1, again, it's another maths question. So 212 million kilograms of aluminium is used for packaging in the UK each year. 68% of aluminium packaging is recycled. Calculate the mass of aluminium that is recycled in the UK every year. We need to work out 68% of 212 million. Now the answer is being given in millions of kilograms. So all we need to do is we need to find 68%. Remember, a percent, remember, comes from the French. Percent is 68 lots of 100 of 212. Put those numbers into your calculator and you're going to end up with 144 million kilograms. That's your answer. 2 nice straightforward marks. You get 1 mark for showing you're working out, 2nd mark for the correct answer. Right, and then we've got another maths question. So drink cans are made from aluminium. I even have to show you a drink can to show you what it looks like. An aluminium can has a mass of 15.8 grams. It's telling you here that there's 1,000 grams in 1 kilogram. So calculate the whole number of aluminium cans that can be made from 4 kilograms of aluminium. Now there's 4 marks up for grabs, which seems very generous. Now the first thing we have to do, we need to convert 4 kilograms into 4,000 grams. Remember, 1 kilogram is 1,000 grams, we've got 4 kilograms, hence the 4,000 grams. Each can takes 15.8 grams of aluminium. So now we just do 4,000 divided by 15.8. Now that comes out as 253.16 cans. Now obviously we're not going to make 0.16 of a can. So look at the question, calculate the whole number of aluminium cans. Well, we're going to have to round down to 253 cans. There's 4 marks, which is a nice, fairly straightforward 4 marks really. Now, where do all the marks come from? Well, you get 1 mark just for converting, 2nd mark for the calculation, 3rd mark for getting that answer, and then the 4th mark for rounding down to the sensible number, like the whole number of cans which can be made. So well done if you got all the marks on that one. All right, and then we're on to a 4-mark question, and we're looking at 3 different methods used to dispose of wood and steel after they've been used. And we have to evaluate the sustainability of the disposal of wood and steel. Now, what you need to do is be talking about the implications of how each material is dealt with. So straight off, less steel is wasted than wood. There's your first point, which means that less space is going to be taken up by landfill by doing that. It's also significant. There's a massive difference. More steel is recycled than wood, and that's a good thing because steel is a non-renewable resource. So we really do need to be recycling it. The other good thing with steel is that no steel is burnt. So it means that there's no carbon dioxide being produced. So it's not contributing to climate change. Now, if you look at wood, one of the downsides is that 58% of the wood is just wasted. So that's going to take up space in landfill. And we're running out of space, remember. Only 36% of the wood is recycled, which isn't great. 6% is burnt, so there's more wood burnt than steel. But unfortunately, that wood is going to be adding carbon dioxide to the atmosphere, which, as we know, is a greenhouse gas and is contributing towards global warming. Now, if you make those points and link what it actually means, you're probably getting into the you will be getting into the 3 to 4 marks. Give a judgment on this one. To me, I'd be talking about the fact that steel is more sustainable because there is so much of it being recycled, at 85%. But as long as you're given a reasoned value, that judgment can push you up into the making sure you get the full 4 marks out of the 4. Right, so that whole question is worth a total of 10 marks. So well done if you got 10 out of 10. All right, so now going on to our organic or carbon chemistry. So we've been told that alkanes and alkenes are hydrocarbons. Define the term hydrocarbon. Well, there's a clue in the name. Hydro, hydrogen, and carbon. So it's a molecule made only of hydrogen and carbon. And that's it. Simple mark. It's one of those definitions you need to know. And then 6.2, we've got our general formula for alkanes is CnH2n plus 2. Determine the formula of an alkane with 10 carbon atoms. So we're being told that N equals 10 in this case. So we're going to have C10, and then to work out the number of hydrogens, it's 2n, so 2 times 10 is 20, plus 2. So you got that 22. So we should have wrote that in there. So that is where your mark is going to come from. Next one, 6.3, we're on to crude oil. So crude oil is a mixture of hydrocarbons, and we've got our fractionating column here. And this is done on a massive industrial scale. Explain how crude oil is separated into fractions. Well, there's plenty of information in this diagram to help you. So first of all, the crude oil is heated. And most of the hydrocarbons are vaporized, turned into gases. Now, the fractionating column, has a temperature gradient, and this is important. So I'm just abbreviating temperature with T. A temperature gradient. It's hottest at the bottom, coolest at the top. So as the hydrocarbons are vaporized, they move into the fractionating column, and they start to, well, depending on the size of the molecule, they start to rise up through the fractionating column. Now, the bigger, heavier fractions, those with the higher boiling points, I should say, or they start to condense at these lower levels. And then the shorter the hydrocarbon, and the ones with the lower boiling points, move further up the fractionating column until they condense at their particular kind of boiling point or condensation point, and then the fractions are just run off. So you're going to get a mark for talking about the heating of the crude oil, another mark for saying that you're vaporizing the hydrocarbons or turning them into gases. You need to make the point that you've got this temperature gradient throughout the fractionating column, and then just talk about the fact that as the different hydrocarbons rise up through the fractionating column, they condense at their particular boiling point, and that's where you get the 4 marks from. Fractional distillation of crude oil comes up frequently. It's a handy question to practice because it does come up a lot. All right, and then we've got an equation to balance. The alkane molecule C14H30 can be cracked to produce smaller molecules. Balance the equation. Now, we've just got to make sure we've got the same number of carbons on the right as we started off with on the left. Now, if you look at that, we've used up 8 of the carbons and 18 of the hydrogens. Well, that leaves us with 6 carbons, and we've got 12 carbons left as well. Well, we're being told we actually get the molecule C3H6, which is propene. Well, we've got to stick a 2 in front there, and that's our equations of balance. Now, there's no spending hours learning how to balance equations, because by now you either get it or you don't. If in doubt, always stick a 2 in the blank, and the vast majority of the time you're going to get the right answer. Alright, so question 6.5, we're being told that propene is an alkene. Describe the test for alkenes. Now again, this question comes up frequently, and it's just one of those things you need to know. The test is bubble the gas through bromine water. Bromine water is like a brown orange color, and the result is, if it is an alkene, the bromine water changes color from orange to colorless. So you could say that alkenes decolorize bromine water. And then question 6.6, polypropene is made from propene. Figure 5 represents a repeating unit. What type of substance is polypropene? Well, there's a clue there with the poly. It's a polymer. So that's the best answer. Now, they would actually accept it's a plastic, because polypropene is a type of plastic. They would even allow hydrocarbon, because it's only made out of carbon and hydrogen as well. But like I said, the best answer is it's a polymer. That question's out of 10, so well done if you got 10 out of 10. And that brings us to the final question. So this is all about rates of reactions. So the student is investigating the effect of changing the particle size of calcium carbonate on the rate of reaction with hydrochloric acid. So you've got the setup here, which is probably quite a common setup that you might have used in school. So you've got your conical flask, you've got your hydrochloric acid, and you've got your calcium carbonate in there as well. And what will happen is that's going to produce carbon dioxide gas. That carbon dioxide gas is going to travel up through the conical flask, through the delivery tube, and it's going to move into the measuring cylinder. Now that measuring cylinder would have started off full of water, and the water gets displaced by the gas. So what you need to be doing is to measure your rate of reaction. We need to be measuring something. So we're going to be measuring the rate at which carbon dioxide gas is being produced. So we're going to be taking measurements of that measuring cylinder every 30 seconds, every minute, and recording the volume of gas produced. And that is our, we could use those results to show the rate of reaction. So how do we set this up? So we're going to need to measure, we're going to use the same volume of hydrochloric acid each time. So we need to measure a volume of hydrochloric acid and talk about the equipment with a measuring cylinder. We're going to measure a mass of calcium carbonate with a balance. So we need to be talking about what equipment to use. Don't assume that the examiner knows what you're talking about if you're just saying measure the mass. Be specific, use a balance. You then add a hydrochloric acid to the calcium carbonate, in the flask. At this point, start your stopwatch. So start a timer, and then record the volume of gas produced. And I would do it every 30 seconds. As long as it's a sensible kind of time scale, they'll still give you credit for it. Now, that is how you do the first test. You would then, I'm just going to write up at the side now, repeat using different size pieces of calcium carbonate. And the important thing here is we've just got to make sure that we're using the same volume and same concentration of hydrochloric acid each time. The fact that we're also making sure that the acid's at the same temperature as well, because if we start changing the temperature, that's adding another variable to our investigation. And then to make this even better, you should get into the habit of just repeating each kind of test 3 times. So again, we can do our repeats, so we can take calculate a mean value for results and highlight anomalies and so on. So there's certain standard things to always put into your method. But if you think about your control variables in particular in this investigation, you'll not go too far wrong. But the other crunch bit is make sure you've got a method of measuring the rate of reaction. So a timer, a stopwatch, has to come in somewhere into your answer. So quite a nice 6 marker, to be fair, compared with some I've seen. And then we're coming to the end of this. So question 7.2, the student investigated the effect of increasing the temperature on the rate of reaction. Explain the effect of increasing the temperature on the rate. Refer to particles and collisions in your answer. So clearly, bit of advice. If you don't include particles and collisions in your answer, you're not getting 3 marks. Now the other thing, typical exam question, explain the effect. Now go for the easy mark. Remember, temperature increases the rate of reaction. So that should be the first point you make. So increasing T increases the rate of reaction. Why is that? Well, the particles, we've used our first keyword, particles have more energy. So therefore, the frequency of collisions also increases. So remember, the frequency, this is the number of collisions per second. So make sure you're getting frequency into there. So we've also got collisions as our keyword. That's where you're going to get your 3 marks. Don't forget the obvious one. Say what happens to the rate of reaction as a result of increasing the temperature. Then say why. Particles have got more energy, they've got a greater store of kinetic energy, they are moving more. So they're more likely to crash into each other, collide with each other. The frequency with which they do that increases. 3 marks. Right, and then we're introducing the idea of catalysts. So catalysts affect the rate of reaction. What is meant by a catalyst? So you've got 2 marks up for grabs. So a catalyst is a substance that increases the rate of a reaction. So it increases the rate. But the second mark, and is not used up during the reaction. So most catalysts you can recycle. Right, so it's important, look at the mark scheme, look at the number of marks, you've got 2 marks. So make sure you're making those 2 points. And then the final answer, this is linking into your biology. 7.4, what are catalysts in biological systems called? They are called enzymes. Nice question to finish on, and that's the last question, is out of 12 marks, so well done if you got 12. Add up your score out of 70 and see how well you've done.